paper called Testing Water Injection Post-Polymer Flooding, a Global Perspective on Project Performance. So I will start from the mechanism. We talk about it a very long time, but we need to start from it. So first mechanism is a viscous fingering caused by a low mobility ratio or the difference between viscosity. So in this example, in this video, we can see very clearly. We can see very clearly once we increase the viscosity, we have a better microscopic sweep efficiency. And next mechanism is related to overcome heterogeneity of the reservoir when you have a hypermobility. In this case, it's the Randy experiments where we have hypermobility 11 times more than low permeability part, and we can see the not good sweep efficiency related to polymer flood, like a piston-like displacement. And here I want to focus on this very interesting case when after the polymer flood, when we start to inject the water. So in this case, it's a secondary polymer flood and tertiary water flood, and we see viscous breaks through the hypermobility part of polymer solution, and even low permeability part have a poor sweep, then it will be a pure water flood. So this main insight driving our paper. So, and we try to open the discussion about what happens when polymer injection is stopped and water injection is resumed. So we have two versions, magical version, which we believe since 1960s, when we believe that residual resistant factor will benefit us during the water flood after polymer injection, and perfectly like a fairy story, the water will push the polymer back from hypermobility part and magically go to low permeability part. Now we know it's not true, and we have a second version which is more logical and have a physical sense. So, and once we can get the answer for this question, then we can go to the next questions. Can the integrity of this polymer slug be preserved? What is the current beliefs and strategies to rationalize behind it? And how does this beliefs impact the design? And are the strategies to mitigate the adverse effects of water injection post-polymer flood? So we did a literature review starting from 1970s and going to up to date, 2024, and I go to bottom line. So many college in 1987 addressed gradient viscosity bank, and some approaches studied on simulations with simplified models and overlooking big data, reservoir heterogeneity, and multiphase dynamics. So we get very good key insights. However, it's have a limited applicability because it's not remaining constrained to homogeneous linear systems without real-world fit application validation. So next I will go through the key factors which we reviewed in our paper. What are the key factors? We mentioned it many times today. So first of all, it's a mobility ratio calculated according to the measurements of relative permeability. Then based on mobility ratio and heterogeneity or permeability contrast, we can use the base case method design developed by Sophie and Seright in 1990s, I guess. And then once we know, okay, as Mr. Delamat mentioned, so optimum viscosity, we don't have a common approach, but even don't think about it. We understand, for example, we need 10 centrifuges of polymer solution optimum. So then once we know the polymer solution viscosity which we need or which we choose it, we go to concentration calculation based on rheology viscosity measurements. Then based on this optimum concentration, we are proving it to record flat test for injectivity, for retention, and so on. But it's important to note that there is no standard protocol among researchers for determining these values. For example, for residual resistance factor, there is no standard per volume injected of water. Someone injected 2 per volume, someone 10, someone 100, someone even more. So next, I would like to discuss the main parameters required in most commercial simulators. So commercial simulators we discussed in rheology, but however, and need polymer retention, residual resistance factor. However, if we cannot use most commercial simulators just using viscosity measurements from the rheometer, then just simply multiply by residual resistance factor. So there is different parts of different directions of knowledge about this and beliefs. For example, Guillaume thinks that we should simply multiply by increase the viscosity at the Newtonian region up to 30%. Someone says it's, for example, Randy says that he had these measurements published in 2011, paper called New Insights into Polymer Rheology, where he proved that viscosity of polymer solution in situ condition will be close to measurements at very low Shea. And someone says, for example, Антуан said that in low permeability rock and high permeability rock, the coefficient which we need to multiply will be different. So there's many different sorts on this thing, but simulator just use a simple way, and doesn't make sense about this. So also polymer retention, we have many different protocols to determine it, and it's also adds some uncertainty. And most importantly, the residual resistance factor. So Randy believes that residual resistance factor is very close to 1 in high permeability condition. And his work, published in 2017, clearly shows that we not inject enough water after polymer injection during our core test, and high residual resistance factor is only a laboratory artifact. So all these values is impacting our simulation and our forecasting, our project, our design, and so on. But even if we see the residual resistance factor equal to 1, it's not benefiting water flood after polymer flood. And if we put inaccessible pore volume equal to 0, we did simulations. So even in this case, so this is the polymer flood gained oil dam after starting here, responded polymer flood. And then here we simulated continuing polymer injection, and blue line here is the chase water flood. And here is this difference between these two lines, cumulative production, only 9%. So when we stop, if we can imagine we just save $millions not to inject the polymer, we just decrease of oil production to 9%. It's very clear that we need to stop. But it's not the case. We believe that if we stop injection, it will go directly to baseline, maybe less. So it showed these results gained from Eclipse 100 or Team Navigator, a simple model, like old model, which shows that this simulation doesn't make sense. That's why it's not a good approach to make analysis or to switch to water. So this is the most important part of our presentation, is the field cases. So as I'm an industry guy, scientist in industry, I will rely more on the actual data which we done on the field, based on trials, pilot injection, rather than mathematical, theoretical calculations, core floods, and so on. So because it's a fact, in Russian we say, fact is fact, мы от этого никуда не идем. So actual data is the actual data, and no matter what the calculations show you, the actual data you should know is the real world. So Woman PPO case, Marmol showed that they have a planned how it goes, downtime, uptime uptime because of some problems, I don't know why. And during this downtime, they have decided to inject the water, maybe to be in the planet voltage replacement ratio ERR, and maybe in other places, but they did water injection, and they call it water alternating polymer injection. In here, blue area, we can see the water injection volume, and during injection of water, we can very quickly deteriorate in oil production, which is clearly showing that we have a viscous breakthrough of water. And then when they turn to polymer viscosity again, they can increase again oil bank. So next is also related to PTO. Next case of this field case of South Oman, and here they did DASS monitoring, DAS monitoring when they see that once they got injection of polymer solution, previously not suited low permeability formation has been swept, and once they again turn into water injection, it will not work and go. And again, when they turn to polymer, soup efficiency increases again. So it's clearly showing that water will just go through the preferentially through the high permeability part. And I would like to introduce a very interesting story about the biggest polymer flood project in the world. It's called in China. So all of you know this guy, Chairman Mao Zedong. And the 1st October is the National Day of the Chinese Republic People's Republic of China, which has been established in 1949, 1st October. Why this date is very important. So first oil from the field comes at the 26th September of 1959, just 5 days before of 10th anniversary of People's Republic of China. And Mao, at this time, it's a new country, it needs resources, it's very poor, no money, and they need oil. And once Mao knows that they opened a big field, huge field, he was so happy, and he said, I will call this field Daqing. So Daqing is the two Chinese characters. First Da, it means big, Qing is celebration. So this field called big celebration. So now you know what this is Daqing. And Daqing is not simply oil field name, because Daqing is the name of the whole complex. And the field actually calling La Sa Xin. La Madien, Sa Ardu, Xin Shuguan, and it's simply called La Sa Xin. So here we have a representative of Daqing oil field who can prove my words. So, as I said, production started in 1959, and they have platinum phase in 1975, and it's only example in this world that it have a platinum phase over 30 years. Can you imagine they produce 50 million stone per year, or how much? We can 300 million barrels per year over the 3 decades. It's astonishing results. And what is the main force behind it? Polymer flood and chemical flooding. So this is a brief result. So can you imagine this? When I see these first numbers, I didn't believe how it can be possible. So they have total number of injectors 35,000, and 15,000 of them is injecting everyday polymer and HC solution. So half of the field under the chemical flooding. And now, up to date, they increase the recovery to 10%, or cumulative EOR production 255 million tons of oil, and overall cumulative production up to 2022 is 2.4 billion of tons of oil. It's a big, huge number. So their geological reserves is between 5 to 6 billions of tons of oil. So Chinese, we can we can say that China is very strong country which can do very brave things and break through in EOR. So this is the map of the Dachshund Lhasa-Hin field. So what they see in Dachshund? They started commercial polymer injection in 1996, and when they typically inject 70 to 100% of pore volume, and they see that water cut stabilizes at about 90%, and when they start to inject the water, after 2% of pore volume, they see the traditional oil production. And again, after injecting 23% of pore volume, water cut increased to 98%. 98% means nothing, only water is recycling. So also they prove that after water injections, it will not be beneficial for water flood, it will deteriorate everything, and no any good results will be achieved. And this is a Kalamkas field in Kazakhstan, where I worked the last 10 years and dedicated my studies for my PhD dissertation. And we had many pilots, and I want to focus on two of them. First pilot is called East pilot. As you see, it's a 9-spot inverted pattern. And Chinese institutes, Chinese Research Center, recommended to make infield drilling to make 9-spot to 5-spot because they proved that in Dachshund field 9-spot is the optimum way to dispose of oil. And the second aim is to decrease the interval distance, because initial distance is about 400 meters, and they decreased it twice in order to see the response earlier. So what they see oil then gained, water cut decreased, and once we injected 50% of water, we was not so experienced. We said, okay, now we can turn to water injection. And I can say here is every point is 1 month, but from the field guys, they called us for the next day, once they turned to water injection, and asked what happened. Our water cuts increased very sharply, our oil decreased to 30%. It was terrible. So then we turned, these facilities existed, and management decided to further expand the polymer flooding, and we turned these 4 wells to polymer flood, and again we see very good oil response, water cut decrease, and we did again, not smart way, we did again to change the water because the economical output was poor, and management decided to turn to water injection in the same field conditions, same geological conditions. We see the same results. Once we turned to water injection, during the first 2 months we lost all oil ban, which proving that water will fingers to the hypermobile part of the high viscous polymer solution. So another case, very famous case of Canadian field, Wilton Lake. This is a primary production, and during they see water flood response quickly, but high water cut increases very sharply. So they recycling a lot of water, and once they do polymer flood in tertiary regime, they see good response, then go to water flood, again deteriorating oil cuts, and again, quaternary polymer flood, and they again gain the polymer bank, but it not achieved previous results, which also clearly showing that water viscous fingering through the polymer bank. So this is conclusions. I will focus on the last one. So what we need to do further? We need advancing our laboratory test accuracy, refining simulation models, like Alan presented, very good results, and validating prediction with real-world data are essential for improving polymer flood strategies and mitigating post-polymer challenges. And also, I would like to focus on the Captain Field case, where Ithaca company, Miss, I forgot your name, sorry. Miss Nancy, she shared with us key insights. The question was, what are you doing when you have shortage of polymer logistics? They said they did not smart way, they tried to change the water, and this is, I think, the same results. We really hope that your company can share this in future publications, and we can update our analysis. Thank you for your attention. So here is my contracts. If we have, I would like to expand our discussions through email, through my phone, LinkedIn, and so on. This is the QR code of my LinkedIn profile. Thank you.
Thank you, Mark, for your nice presentation. Now we have one or two questions.
Hey, thank you, Mark. Very interesting. It's just a comment. I think I've really learned a lot from all these presentations this morning. And I was just thinking of the last two. You know, in one case where you say you just stop and your polymer flow and you go to water, and then probably all your viscous crossflow stops. And maybe, you know, the tapering, you know, you keep some viscous crossflow going, right? And the thing that really struck me was the 3 centipoise against the 2,000 centipoise oil was almost as good as the 60 centipoise against the 2,000. So this argues, you know, you really do want to taper. If you got like 50 tons of polymer left, you don't want to just use it and stop. You want to kind of, because you just keep your viscous crossflow going. Maybe it's not as dominant at the higher viscosity, but I don't know, that's something that I don't know if that's correct or not, but that's just, you know, kind of tying the last two talks together.
Yeah, it's, you have a correct part. So if you see this slide, so here we did, in this case we created polymer bank as the last 2 months, and here we didn't create a polymer bank. So we based on our previous experience, we tried to mitigate water break. So it helped a little bit because you can see the oil bank decreased only up 2 months. But in the first phase, when we didn't grade it, it's go down for the first week, water injection. So it's mitigated. So as my conclusion, I said we need to more investigate this kind of approaches to mitigate bad results of water injection.
Yes.
Good one, thank you.
Catherine Kuna, Norfolk, Alaska. You demonstrated in all of these fields very powerful and clear examples of switching to water, you're done. It's a not good result. So this is not a summer trend. I think we're all, considering this. Tapering looks like it may be a very cool thing. Do you know if any of the fields are planning to use a much lower viscosity polymer or replicate that tapering over a long period of time to test the results in the field?
Unfortunately, I don't know.
Okay.
Good point to testing.
Maybe a comment on tapering. There have been some work done in 70 to 8 universities. It's really evolving time. Because how large is the bank, how far do you decrease? So this is where some work, a lot of work has to be done. We need some help because what we see is when you have a sharp hole, it's done. But the question is when do you decide to stop and why? And I don't think there's an answer. I don't think it would be easy to find out. But clearly what we see is the enemy and tapper. The question is when. So it's flexibility, and what it shows also is 30% more volume, 50% more volume, 60% more volume. It doesn't make sense because it has a huge impact on selecting the polymer. If you offshore, for instance, and you say, when I switch to water, the water will push my polymer, so I choose a very expensive polymer, so it will keep pushing when I push to water. It doesn't make sense. What you need behind the polymer is not residence time, it's injection duration. If you overkill the design, if you choose a polymer